Hi, and welcome to the third video of short course module number 2, wherein we'll discuss some of the more technical details of conformational searching. And so I just want to, make a disclaimer, I guess, right up front that I'm not going to show you everything about MacroModel or Maestro, and I won't show you all of the features, but I'll try to give just a brief introduction into how you might be able to use this program to do a conformational search. And so, again, there are other programs and other methods that are comparable, both commercial and free, and there are many features and settings that I won't cover here. But in general, sort of the most important thing is that in general, when we run these calculations, we use the OPLS-3E force field, and we generally do these in the gas phase, although there are instances where you might be curious to see what happens when introducing solvent. And so, how exactly might we start up MacroModel? And so this requires a connection to the group computer, which runs Linux. And right now we're using TeamViewer and a reservation system in order to access this computer. And so you open up a terminal window and you type $Schrodinger /maestro-sgl. If that's not available to you, you can usually just arrow up if that terminal window has been used before to access Maestro. And it should open up a Scratch project, and you can open and save the project as you see fit. But generally, I'd recommend saving projects and not using a Scratch project. There are a couple ways that you can build a molecule. So one way is you can use this sort of building tool that's up at the top corner. So you can I've added a benzene ring here. But you can also view this in a 2D sketcher, which is essentially just like ChemDraw. So you can erase and draw just the same way you would with ChemDraw. Sometimes it's a little laggy. And in this case, I'm just going to use the example of triethylphosphine. And I'll show how we can build this molecule in two different ways. So the first way is in this 2D sketcher. And I would like to note that it's important to update entry or to save as new, depending on what you want. And so you can see I have a nice 3D structure of triethylphosphine there, but I can also import structures from the file menu. And so in this case, I'm going to my folder within the group Dropbox. And I am looking for, I uploaded a file that you can generate in other sort of programs, and so I generated what's called an SDF file, which gives the 3D coordinates of a particular structure. So you can see I've uploaded the same structure. There's really no difference between them. And then now what I want to do is do a conformational search. And so you go to tasks, and you can either search or it's usually one of the most recent ones. Again, you sort of choose OPLS-3E and change the solvent to none. And then there are also other options where you can add constraints or consider a substructure of a molecule. And then in general here, I change the maximum iterations. This is more important for flexible molecules, and I change the convergence threshold. And one other important thing is that's the energy threshold. So I will only get conformers within a 5.02 kcal per mole window. And we use that window because molecular mechanics energies aren't so accurate. So we just hit run, and it's important to see that little circle is starting to sort of buffer, and then you can check the job status here and make sure that it's running, and then we'll just wait for this to finish. And since this is a small molecule with relatively few rotatable bonds, this should be pretty fast to incorporate our different conformers into this project. And so that's finished. See, it was really fast. See, the status has changed from running to incorporated finished. And then we have a bunch of different conformers here. We can see they all, differ through rotations of the ethyl groups. And we can look at the table and we can export all of these or a subset depending on, how you want to select your conformers, which is sort of an ongoing area of research in the group. You hit this export structures and then navigate to the folder that you would want to save these to. And then there are a couple options for saving. You can export them all to the same file or individually. You can use just the entry titles, or you can export each group individually. It sort of depends on how you want to process these conformers later. And I know there are a couple of different ways in the group of doing this, but it's important to make sure that these are sort of saved usually in the SDF file format, because that's really broadly compatible with a lot of different programs and a lot of the different scripts that are used within the group. And so you can save that. I'll cancel just because I don't need to save these. But that is basically how you can use MacroModel. It's important to either save your Scratch project or make sure to close your Scratch project and then exit out of your TeamViewer session. And then you have your conformers that you've selected, and then you can submit those for DFT optimization using the program Gaussian, which I will discuss in a different video. And so with that, I'd encourage you to either move forward to the fourth video in the module, which is an introduction to DFT, or to move directly to how you submit these conformers in the case that you've already watched the introduction to DFT video.